Hello everyone, I am Professor Mrs. Deepa Bhandare, presenting video lecture on frequency response analysis. Points will be covered under frequency response analysis basics are introduction, advantages of a frequency response, then concept of frequency response, then plotting of frequency response and frequency domain specifications. In introduction, in time domain analysis, various standard test inputs like impulse, step, and ramp functions are used to study the performance of control system. From the step response of a second order system, we can find time domain specification like peak overshoot, peak time, rise time, and steady state error. But the extraction of a transfer function from the step response is very difficult since it is a laborious. On the other hand, using the frequency response method, we can easily obtain the transfer function from the experimental data. The frequency response of a system is the response of the system for sinusoidal input signal of various frequencies. In general, the sinusoidal test signal is given by as shown in figure. Here, this is the input signal RT and the magnitude of this sinusoidal input signal is A. The graph is plotted between the magnitude of the input signal A versus the time on a x-axis. The standard sinusoidal input signal as shown in figure RT is given by equation RT equal to A sin omega t, where A is the magnitude of the input signal and omega is the frequency of oscillation. Normally, A is kept constant to obtain frequency response. For this standard sinusoidal input signal, the system gives steady state output, that is Ct, and Ct is given by equation Ct equal to B sin omega t plus phi, where B is the magnitude of the output, omega is the frequency of oscillation, and phi is the phase shift between input and output. The relationship between sinusoidal input RT and steady state sinusoidal output CT of the system in the frequency domain is known as frequency response. Point number 2, advantages of frequency response. First, transfer function of the system can be carried out from the frequency response. Next, design of the system and adjusting the parameter of the system can be carried out easily in frequency domain. Next, corrective measurement for noise disturbance generated in the system. Next, absolute and relative stability of the closed loop system can be estimated from the knowledge of the open loop frequency system. Next, frequency domain analysis can be also carried out for the nonlinear control system. Point number 3, concept of frequency response. It deals with the response of the system when a sinusoidal input is provided to it. Let us consider a linear time invariant system with open loop transfer function is GS. It is a stable linear time invariant system and seesaw dynamic system. The block diagram representation of GS is as shown is here. Input applied to GS system is RS and output getting from a GS block is a CS. Let RT and CT are the input and output signals of the system. Now we have to prove that for a sinusoidal input, the output at steady state also be a sinusoidal of the same frequency but with different magnitude and phase angle. The steady state response of a stable linear time invariant system to a sinusoidal input does not depend on a initial condition, and so we can write the output CS as CS is equal to GS into RS. Mark this is as equation number 1. Let the input be RT equal to A sin omega t. Mark this equation as 2. Then we have RS is equal to A omega upon S square plus omega square. Mark this equation number 3. Then substituting equation number 3 in equation number 1, we get CS is equal to A omega upon S square plus omega square into GS. Mark this equation as 4. Splitting equation number 4 into partial fractions, so we can write CS equal to K upon S plus J omega plus K star upon S minus J omega per plus partial fraction terms of GS. First two terms are due to the poles of input RS. Partial fraction terms of GS are due to the poles of the transfer function. The first two terms we can call it as steady state response CSS. Then partial fraction terms of a GS we can call it as a transient response CT. Here K star is a complex conjugate of K. The complex poles results complex conjugate coefficients. The output contain transient component and steady state components. For the steady state stable system, the transient components die out while steady state components exist forever. So, we are interested in steady state performance analysis. So, let us neglect the transient components. Then only consider the steady state response, and steady state response is given by CSS equal to K upon S plus J omega plus K star upon S minus J omega. Taking Laplace inverse on both sides, we get Ct equal to A magnitude G J omega into e raised to j omega t plus phi minus e raised to minus j omega t plus phi upon 2j equal to a magnitude g j omega into sin omega t plus phi omega equal to b omega into sin omega t plus phi omega, where b omega equal to a magnitude g j omega. Therefore, the steady state response of the system for a sinusoidal input of a frequency omega is a sinusoidal output with a magnitude b omega and phase shift phi omega as shown in figure. Figure shows sinusoidal response of a system GS. In this figure, the steady state response of the system for a sinusoidal input of a frequency omega is a sinusoidal output with a magnitude b omega and phase shift phi omega. The amplitude ratio is given by magnitude g j omega is equal to b omega upon a. The sinusoidal transfer function g j omega can be obtained by substituting s is equal to j omega. So we get g j omega is equal to c j omega upon r j omega. Therefore, magnitude g j omega is equal to magnitude c j omega upon magnitude r j omega, and phase shift phi omega is equal to angle g j omega equal to angle c j omega upon angle r j omega. In general, magnitude g j omega and phi omega vary as the frequency varies. Point number 4, plotting frequency response. The frequency response of a linear time invariant system can be obtained by applying a spectrum of input sinusoidal to the system. We have already studied that when a sinusoidal signal a sin omega t is applied to the system, the steady state output also a sinusoidal signal with the change in a magnitude and phase given by Ct equal to A G J omega sin omega t equal to A magnitude G J omega into e raised to j angle G J omega sin omega t, where G J omega is equal to magnitude G J omega e raised to G at an angle G J omega. This is in a polar form. Generally, the value of A is equal to 1. Therefore, the magnitude is equal to magnitude G J omega and phase is equal to angle G J omega. Next is point number 5, plotting frequency response examples. Here we have taken two examples that are draw the frequency response of the following system. First example is Gs is equal to 1 upon 1 plus 2s. It is a first order system. So how to get the solution for this? First of all, you have to put s is equal to j omega. Therefore, sinusoidal transfer function is g j omega is equal to 1 upon 1 plus 2 j omega. Therefore, the magnitude of the response is magnitude g j omega is equal to 1 upon square root of 1 plus 4 omega square, and the phase response is angle g j omega is equal to minus tan inverse 2 omega. Now we have to plot magnitude g j omega versus omega is known as a magnitude response, and plot of a angle g j omega versus omega is known as a phase response. So now vary the frequency omega from 0 to infinity and tabulate the values of magnitude g j omega and angle g j omega. So this is the table we have to make. We have to vary the frequency omega from 0 to infinity. So figure shows the frequency response of the system Gs is equal to 1 upon 1 plus 2s. This is the magnitude plot, magnitude g j omega versus omega, and this is the phase plot. Figure B is the phase plot, figure A is the magnitude plot. Phase plot is the angle of g j omega versus your frequency of oscillation. On a similar line, let us draw the frequency response of the system Gs is equal to 1 upon s square plus 2s plus 4. So put s is equal to j omega. So the sinusoidal transfer function is given as g j omega equal to 1 upon minus omega square plus 2 j j omega plus 4. So the magnitude response is magnitude g j omega equal to 1 upon square root of 4 minus omega square, again bracket square, plus 4 omega square, and the phase response is angle of jj omega is equal to minus tan inverse 2 omega upon 4 minus omega square. So again make a table and vary the omega from 0 to infinity and tabulate all the values of the magnitude jj omega with respect to omega's values, and also get the values of phase angle g j omega with respect to omega from 0 to infinity. The angle g j omega is in a degree form. Figure shows the frequency response of the system Gs is equal to 1 upon s square plus 2s plus 4. So figure A is shows the magnitude plot, magnitude G J omega versus frequency omega, and the phase plot, the angle G J omega versus the frequency omega. So this is the phase plot, figure B. Figure is the magnitude plot. Point number 7, frequency domain specification. Following specifications are used to measure the performance characteristics of a system in a frequency domain. First is resonant frequency omega r, second is the resonant peak mr, third is cutoff frequency omega c, fourth one is the bandwidth, fifth is the cutoff rate, sixth is the gain margin, and seventh is the phase margin. First five characteristics are closed loop characteristic, and remaining two, that is the gain margin and phase margin, are open loop characteristics. Resonant frequency omega r is defined as the frequency at which the output of a system has a maximum magnitude is known as a resonant frequency. Resonant peak mr is maximum value of magnitude is known as a resonant peak. Cutoff frequency omega c, the frequency at which magnitude g j omega is 1 upon root 2 times its maximum value is known as a cutoff frequency. In other words, the frequency at which magnitude of a closed loop system is 3 dB less than its maximum value is called cutoff frequency. The next is a bandwidth. In feedback control system, the range of frequency during which the magnitude m is greater than or equal to mr upon root 2 is defined as a bandwidth omega b. Note that the plot is exist for positive value of omega only. So the bandwidth of this control system is from 0 to omega c, or simply omega c. Next is the cutoff rate. The cutoff rate is the rate at which the slope of magnitude at the cutoff frequency. Here figure shows magnitude response of a control. So the figure shows magnitude plot of a typical control system, that is magnitude G is omega versus log omega. Note that plot exists for positive value of omega only. Resonant frequency is omega r. Resonant peak is a mr, and this is the bandwidth, and this is the WC, that is the cutoff rate. In other words, we can say the cutoff rate is the slope of frequency response near the cutoff frequency as shown in figure. Note that the frequency is in a radian per second. Thank you everyone. Hope you like the video on frequency response analysis basics. If you have any query, please contact me. Thank you very much.